Alright, so what I'm going to do in this video is show two problems involving KSPs. One is called the common ion effect, and it's how having a common ion in a solution, an ion that comes from a different source, okay, will have the solubility of a slightly soluble compound like calcium fluoride in this example. And the second problem will be predicting whether or not a precipitate will occur. And then in another video we'll get into a much more extensive problem which will incorporate some of these skills. Alright, so let's talk about what we have here. What we're assuming here is that we have a solution of NaF already made up, and it's got a concentration of 0.025 molar. And because NaF has one sodium, one fluoride, and by the way, I'm not even giving the KSP because things that we said were soluble earlier in the year have really large KSPs. Essentially, the dissolving process goes to completion unless the solution is saturated. Group 1 metals can make pretty concentrated solutions, so sodium fluoride or chloride or any group 1 halides are going to be very soluble. So basically, you can assume that you have 0.025 molar concentration of Na plus and 0.025 molar concentration of F minus. We don't care about the Na plus. It's merely a spectator in the process because it's not going to be part of the expression. What's really important here is what is the calcium fluoride equation, because that's the one that we have the KSP for, right? So the equation will be Ca2 plus Aq plus 2F minus with the Aq next to it there. And the KSP value will just be, the calcium concentration times the fluoride concentration to the second power. So we've got our two equations, and now I got an ice table. Now, again, unless they ask me, how much of it's going to dissolve, right? So you could determine how much solid calcium fluoride will dissolve if they ask you that question, as long if you know how many moles of calcium ions that you get in a particular situation. But they're not going to involve any of the equilibrium calculations. So in the ice table, I'm just going to X this guy out. And the difference with this one is, while I'm going to start with 0 for my calcium ions, I'm going to start with 0.025 for my fluorides, because what I'm really doing is I'm trying to add some calcium fluoride to this beaker or this test tube, and we're going to talk about how much of that calcium fluoride is going to dissolve and how much of that calcium fluoride is going to end up as a solid in the bottom of the beaker. Because if we get the saturation right, that's what we're really doing here. We're saying, okay, if we drop enough calcium fluoride in so that all of it dissolves, it can dissolve, what's the concentration of those ions in there at that point? And that will tell you, if you know how much the concentration of calcium is, you also know how many moles of calcium fluoride dissolve. So we can assume that this is going to go up by X as some calcium fluoride dissolves, and we're going to assume this is going to go up by 2X. So this will be X, and this will be 0.025 plus 2X. Now, again, we can do the math with our new fancy calculator, and we can solve for X by plugging everything in, because we essentially get this. We get 4 times 10 to the minus 11, right, equals X times 0.025 plus 2X. But I'm going to assume that the amount that just compared to how much is already in there, considering how small this KSP value is, that the amount of actually extra fluoride ions that are going to be added to the 0.025 is going to be negligible, or at least less than 5%. So when I do the math here, I just do this number here is equal to X times basically 0.025. Forgot the second power there. Second power. Okay, and when I solve for X, what I get as a value here is I get 6.4 times 10 to the minus 8, which means 2X is basically 12.8 times 10 to the minus 8, which is a lot smaller than 0.025. This is 2.5 times 10 to the minus 2. This is to the minus 8. This is 6 orders of magnitude smaller. So you can even just write a sentence and say 12.8 times 10 to the minus 8 is 6 orders of magnitude smaller than 2.5 times 10 to the minus 2, which means it's a lot less than 5% change. So the assumption is valid. Now, and so when this X is the molar solubility, molarity, moles per liter. That would be the number of moles of this substance, calcium fluoride, that would dissolve in a liter of solution. Okay, and we could also use that as a smaller volume solution. Let's say it was 500 milliliters, we'd be half that number of moles. All right, another type of problem we'd have to do here would be to predict whether a precipitate will occur. These are kind of annoying because they involve a dilution, because you're going to be mixing two solutions, okay, which means you think you have the molarities, but you have to calculate the new molarity. So for those who don't remember how this whole thing goes, basically we have a situation in which we have cerium iodate, and that's its KSP. And we have cerium nitrate, very soluble because it's a nitrate, potassium iodate, very soluble because it's a potassium salt. And we're given the concentrations to begin with, and we're going to mix the two, and we assume that the volumes are additive. That's a really important assumption, right? Which means the total volume is going to be 1,050 milliliters, right? And so we can then do our little dilution calculation. Now, in case you forgot how a dilution works, it's basically molarity 1 times volume 1 equals molarity 2 times volume 2, all right? And the new volume is not the other volume, it's the total. So this is really volume total, right? Right? But then you end up cross multiplying, so what ends up happening basically is you do, like, for the first one, 750.0 milliliters times the original molarity, which is 4.00, times 10 to the minus third, over, and that's in molarity again, the new volume, which would be 1,050 milliliters. And here's the problem with this one. Now the good thing is, because we're interested in the cerium, there's only one here. Otherwise, we have to take into account, like, the formula here. And it's very important you recognize that for every 1 mole of that stuff that goes in, you get 1 mole of cerium ions. So this is going to give you the concentration of cerium ions in our new solution, which is equal to 2.86 times 10 to the minus 3. You do the exact same thing with the other one, so you have basically 300.0 times 2.00 times 10 to the minus 2. And again, we're interested in iodate, and there's a 1-to-1 ratio here, so the concentration of the solute is also the concentration of the iodate ions. Does not have to be the case, so be careful with things with like a parentheses 2 in them or something like that. That's going to throw you off. Over the 1,050 milliliters. Again, the milliliters are going to cancel out, so you'll get, your answer in molarity, and the concentration of the iodates here is going to be equal to 5.7. Let me write the iodate is equal to 5.71 times 10 to the minus 3. Now, basically, once you have these concentrations, you compare Q and you compare K. If Q is bigger than K, that means it's going to shift back to the left. Because think about this equation. The equation here is, here's cerium iodate, right? Cerium iodate would be Ce IO, right? 3 with a 2 right there. Was it a 2 or 3 there on that? I got to make sure I got the right formula here. It's a 3. That's really important. Okay, and that's going to be equal to the cerium concentration plus 3 times the IO3 AQ. So we have to, right, so we can now, once we set this up, if we have the KSP value, we can see if Q is greater than K, because the essential idea is if Q is greater than K, it's going to shift to the left. If Q is smaller than K, it's going to shift to the right, which means more of it will dissolve, basically. Or you could add more and it will dissolve, okay? So if Q is greater than K, we're going to get a precipitate. And by the way, if we get that, then we can ask other problems like how much will precipitate, what mass will precipitate, and they will definitely ask those things on the AP exam. Okay, so our formula is basically this. We have 1.9 times 10 to the minus 10, right, is K, but we don't want to solve for that. We're going to solve for Q. So we're going to see if we get here is, I'm going to redo this. I'm going to stop. Okay, so what you can see here is I've written Q is equal to this, and we're going to see whether the value we get for Q is greater than or less than K. If it's greater, it's going to shift to the left, which means it will precipitate out. We'll get some solid precipitate. If it's smaller, we don't. So the values we have here for the, we're going to use these values over here, which I'm checking off right now. We're going to use the 2.86 times 10 to the minus 3 to the first power times, and we can put the big molar in there if we want. That's important, okay? And then we can put the 5.71 times 10 to the minus 3 to the third power in the second bracket. That's the iodate concentration. And when we do this, we get a value of 5.32 times 10 to the minus 10. Now this value, 5.32 times 10, it's not much bigger, but it is bigger, okay, than 1.9 times 10 to the minus 10. And this means we will, in fact, have a precipitate.